Okay, I think we're ready. Today we're going to do shaft deflection, so bending shafts and things like that. We'll do this in SolidWorks so that it's actually going to be a computer simulation. We'll end up with something like this. We're going to do a different shaft than this one, but I just had that picture so we can put it on the thumbnail. But we'll do something like that. This actual one that I'm showing here, it's a stepped shaft also. It has a large section, a smaller section. So even it would be a little bit tough to do by hand. If you have a solid shaft that doesn't change diameter anywhere, then you could just do this with a beam deflection equation and be simply done by hand. But once they have steps in them, the larger sections and smaller sections, then it becomes a little bit tougher to go in there and do that by hand. There are methods to do it. Your book doesn't even really present a method to do it by hand, other than by a beam calculation. But we're going to use SolidWorks. Now, you don't have to account for every little detail like the fillets or a ring groove or things like that. Those little smaller details don't have to be accounted for when you're doing deflection. They're the things that most count when you're doing stress concentrations and stress in the beam or in the shaft. But when you're doing deflection, you really just need the gross geometry of the thing. So you don't have to go model in all of the little details like that. In fact, if you do model those in, they're probably going to make your your simulation a little susceptible to some continuity errors or some errors, unless you have a really fine mesh or you know how to create a variable mesh with finer mesh around those small details and coarser mesh elsewhere. So I would just leave them off. Even if they're not difficult to model in SolidWorks, I would leave them off for the meshing purpose and just use the gross geometry of the shaft. So what we're going to do, let me pull up SolidWorks here. Let me find it. I've already built this. So I haven't posted where you can get these. Actually, these gears and the bearings, I just grabbed those from McMaster. So I assume you know or have already done things like this, but just in case you don't, there are sites, this is mcmaster-carr, but there are other sites that I'm not thinking of their name of right now. GrabCAD is a good one, where all sorts of machine elements are modeled already. So mcmaster-carr, the good thing about it is that here's the gear you want to buy. So $30 gear or whatever. I think I used these two, the 16 pitch and then the 24 tooth and the 48 tooth gear. I think those are the two I grabbed. But you can just click on the part number here for it, and this product detail, most all of them will have this little symbol that says CAD. And if you click on the product detail, you can download the CAD model for a variety of things. SolidWorks is one of those. And then these others are like, there's some 2D drawings if you want just the 2D geometry for a layout. And then there's all sorts of generic ones. There's even PDF. I haven't looked at that one before, 3D PDF, but that might be a useful way for getting the item into a report or something like that. But it defaults to SolidWorks, or at least it did for me. And you can download it, and you have the SolidWorks file that you can use to, I suppose you could print the file if you wanted to go 3D print the part, but I just use these for going in and dropping them into SolidWorks. And so that's what this gear, and actually these are the two same gears. I just rearranged them. So this is kind of like a double reduction gearbox or something. And then the same thing I did with the roller bearings over here. I just grabbed these from McMaster. One thing that these do show, let's see, I think the roller bearings probably show it easier. Last time we were talking about the fillet radius and how it couldn't be just this huge radius, even though that does reduce the stress concentrations. You can't have that huge radius because the element, in this case the bearing, has to sit up against the shoulder. And so how they do that is, we zoom really in, you can kind of see this little chamfer right here. That chamfer is giving clearance for the radius. So assuming you know this chamfer, then you know the amount of radius that you can have on those steps. And these gears have that same thing in their hub also. There's a little chamfer. And so that'll let you know how much radius you can have. That's not the point of what we're doing today, though. We are looking at this kind of setup. So the idea here is, I actually have it where we can draw on it over here. The idea is that we will have an input torque on this lower left shaft. So that'll be our input torque. You know, maybe something, I'm drawing with a mouse, so it's not going to be great. Something like this. And I'm going to make that 10 foot-pounds. So relatively small input torque, but these are relatively thin and long. For this jack shaft over here is relatively thin and long. So we can't have too much torque. In fact, this might be too much once we do the analysis. But 10 foot-pounds, I'm not going to try to write that. I'll write it on paper once we get to that point of torque coming in here. These gears are a 2-to-1 ratio. So this larger gear, if we look at our McMaster page, well, let's go back a page. Here, zoomed out. They have pitch diameter of 1.5 inch for the smaller one and 3 inch for the larger one. Or you can look at the number of teeth, 24 to 48, and see that they're a 2-to-1 ratio. Those are the two gears that I use. They're just regular spur gears with a hub on them. So if I have 10 foot-pounds of torque here as an input torque, then I'll multiply that by 2-to-1 to get to the next shaft, because I'm reducing the speed and multiplying the torque. So this gear is going to be rotating. If this one is spinning, I've tried to draw that clockwise, I guess. So this one would go counterclockwise, and then see how there we go. That would mean this one's also going that same speed and torque and direction. We're assuming there's no losses in this shaft. You know, the bearings are not frictionless. They are frictionless, but they're not without friction. Frictionless is that they have less friction than some other method. But they are not without friction. And so this guy is going to be spinning this way. And this larger gear on the short shaft is going to be our output shaft. All right. And so we're not interested in the input or output shafts. We're interested in the shaft up here with the two gears on that single shaft. And we're only interested in deflection today. So we want to know, how much is this thing going to deflect? So I've already modeled it. Let's go to the model. We might need to come back to that. I don't know. We'll leave it there for now. So here's our model. Let's find the model of just the shaft so we can look at it. I think it's this one. Yeah, that looks like it. All right. So I've got a couple of things going on here. First of all, I didn't put fillets on it. I didn't worry with that. I didn't put any kind of ring groove to retain the gears. Maybe those gears didn't actually show any sort of retaining mechanism at all. They don't have a set screw. I don't even think they had a key in them for torque transfer. So they probably, I don't know, maybe they're designed for a press fit, but we're not too worried with that part yet. On Monday, we'll talk about torque transfer and elements to locate elements such as the gears and pulleys and all that. We'll talk about that on Monday. So I don't have any fillets. I do have some steps, so you can kind of see this is where the bearing is going to ride on one end, and here it is on the other end. And then there's a step there that you have to be careful with this step. In fact, let's go back to is this it? The assembly? Yeah. So let's look at this side. What you don't want to happen is have that shoulder so large that it contacts the outer race on the bearing. So you can kind of see, I could make this shoulder quite a bit bigger, in fact, if I wanted to, and still only contact this inner race. We'll talk about ball bearings at a later time also, and mention that again. But if I had this shoulder so large that it was making contact with the outer race, then I've locked up my bearing and it can't do what it's supposed to do. So you do have to be careful with that. Let's go back here. So there's the little shoulder, and again, I can make that somewhat larger, but not a lot larger. I think this is a 1/2 inch diameter, and then this is 5/8, I think. Same thing over here. Now, this one's not as big of a deal because it's just up against the gear, which in this case, you actually do want the gear and the shaft to sync together. You want to be able to transfer torque. So if anything, this is helping me transfer torque. But it could be a little bit larger, but it doesn't have to be, at least not to locate the gear. It does have to be large enough that it doesn't sit down inside that chamfer in the gear, in the hub of the gear. But other than that, it's not going to need to be any larger for this purpose. It might need to be larger for deflection or stress purposes. So that's pretty standard. And then I think I made it, this is a 1/2 inch by 1/2 inch. I think this is 3 inches long. I think that's 4 inches, and another 3 and another 1/2 inch, I think. We could go measure it. I just don't remember it. Or actually, we could look at it right here, I think. Yeah, 1/2 inch, 5 inches in the center section. All right. I just made the shaft with a revolution. Now, the other thing that I've done here to set up for the simulation is I have split it. So you can see these little split lines on it in various places. So I don't necessarily need this split. Well, I will later on, but to apply the loads and everything, I don't need this split line. What I've done with this split line, this piece, this one, and the matching two there and there. Those I'm going to use as a way to measure the deflection once I do the simulation. So I'm going to measure the deflection on that line. So that line starts out horizontal, and then it gets all twisted out of shape by the gears pushing on it. Here I've isolated the bearing so that I can create that. And now this one, the shoulder naturally isolates it anyway. But I have a area here, surface, well, there we go, that I can fix as a bearing fixture in the simulation. And then here, this split line is more or less where the hub ends on the gear. So I'm going to apply any forces that the gear experiences. I'm going to apply them to this and this surface. So that's why this split line and that one are here. And I created the split lines in SolidWorks with I created a reference frame. So if I go to features, let's just make one real quick. Reference geometry, a plane, and we'll make it parallel to this, and we'll make it, where did it put it? Put it over there. Let's flip it the other way. So there, maybe if I wanted a split line right there, I could generate a plane on that surface, and then I could do curves and split line. Whoops, I skipped off of it. Curves and split line. And then you select, in the pink box, you select what's going to do the cutting. And in the blue box, you select what's going to be cut. And then you check, and then I've got that split line right there. Now, I don't actually want that. So they don't have any effect on the deflection or stress or anything. But it splits up surfaces so that you can do things in just certain locations. Sometimes you need that when in the simulation to apply a load at a certain point or something like that. And that's what I'm using them for. All right, so other than this, I showed you this already, but other than that, all we did was, let's look at it from this side, is build the profile and revolved it around this axis down here. So it just did a revolution. That's all it was. Yes. All right. So there's our shaft, ready to go. So we go to simulation. Now, if you don't have your simulation tab open already, I believe it's in tools and add-ins. You can add in, where is it at? There's flows, no, form, cam. Oh, maybe it's already, maybe it automatically loads up now. It used to not automatically load up, but I don't see it separately anymore. I see the flow simulation separate, but I don't see the simulation one separately. Oh, there it is, right there. It's just in the premium add-in section. All right, so you have to check this on. You don't necessarily always want these, like The marketplace, that's another place you can get parts. I actually don't want that because I usually just go get them from McMaster. But there is a marketplace where you can go get SolidWorks parts files. The cam, probably don't need that one either because that, unless you're about to do some cam machining, CNC machining work, don't really need that. Don't really necessarily need the form. So these have an impact on the overhead required to run SolidWorks, memory overhead and startup time and stuff like that. So if you want to speed things up a little bit, you can turn some of these that you don't use, you can turn them off and unload them, or don't load them when SolidWorks starts. All right, but we do want, oh great, now it's going to have to, it's going to have to adjust those settings. I shouldn't have clicked anything. There we go. All right. So if you do want simulation, you do have to make sure that one's checked, though. We're going to do a new study. There are all sorts of studies that you can do. Static is what you end up doing most of the time, but there are others. These design and topology studies are really cool. The topology study lets you do some generative type of, not machining, but modeling, so that you put some constraints in, and SolidWorks goes and figures out only the material that you need to support those loads. But we're just going to do a regular static study. All right. One thing that I didn't mention, but we have to do is the material has to be defined. If we don't define a material on this shaft, then it can't do any of the simulation. So it's still loading up this study right now. I think it's ready now. I have the plain carbon steel loaded up already on this material, on the shaft as its material. So that's the first thing you have to do. If you didn't define the material when you built the part, then you need to define the material now. Then you kind of just go in order. There is an order across the top here also, but I usually use this and go top to bottom. Now, you might get confused. In connections, there are bearings, but and you can do it this way. In this case, it's simpler to, instead of doing the connections bearing support, do a fixture. I'm right clicking to bring up these menus, by the way. I click on it and right click. Do the bearing fixture. That's going to be simpler for what we need to do, because we're not actually interested in the bearing. We just want to have the effect of the bearing. So I'm going to click bearing fixture, and then it's going to bring up a menu over here shortly. There it goes. And this blue box is what surface does the bearing ride on. So that's why I want this isolated. You can't do two at a time. You can only do one at a time. So pick one of them. We do want to allow self-alignment. If we don't allow self-alignment, that holds that piece of the shaft perfectly, in this case horizontal, but we want to see what the shaft would do if it were allowed to, because these bearings have a limited amount of slope that they can handle. And so in your books right here, this is page 371 for the 10th edition. These are spherical ball bearings. They can only handle, these are in radians, so 0.026 to 0.052 radians. So that's just a few degrees, 2 degrees or so. Maybe at the very high end, maybe it's 3 or 4 degrees. But they can't handle too much of slope. Others can handle more, others can handle less. There are, well, this doesn't show an articulating bearing, but there are bearings that can articulate a little bit and have even more allowance for slope. Well, it does have the self-aligning ball bearing, and it looks like they have basically the same allowances for as the spherical ball bearing. So we have a limit on how much slope we can allow at the bearings. So I want to see how much can the bearing, or how much is the shaft wanting to slope. So I'm going to allow self-alignment. I'm not going to put in any sort of stiffness measurements here, but you can if you want to. Maybe you know something about how rigidly mounted the bearings are, and you can adjust that here. I do want to stabilize shaft rotation. If I don't do that, then the shaft in the simulation is going to have trouble resolving. It may not resolve at all because the shaft is going to want to spin as well, and there's nothing stopping it from spinning. So I'm going to stabilize shaft rotation. All right, and I'm going to let me turn on the view. Let's see, display. No, hide and show. Let's unhide all the types. Can I do that? Well. Maybe it's just being really slow. There we go. I just want that to so I can see the progress as I go along, and I'll hide it later. We didn't need to do that same exact thing again. So a fixture, bearing fixture, let it load up. Put it on the other end, allow self-alignment, stabilize shaft rotation, and now those two bearings that we had modeled are acting out here. Now if I wanted to use the actual bearings, then that's when I need to do the connections, and that's going to create the bearing based on the geometry of the bearing model itself. I'm not interested in all that. I just want the effect of the bearing, so I'm just doing the fixture. External loads. All right, so now we've got to do some math. So let's close this out and go over here. All right, well, first, let's get in our mind what the assembly looked like. No, it's asking me to rebuild the model since I've changed stuff. We may have to go back and redo our simulation, but that's okay. We didn't do much. All right, so this is kind of how this thing is set up. You can kind of see here there is going to be contact between the pinion and the gear, and in this case maybe 1.5 tooth of contact total. You know, I didn't perfectly align these, I just kind of put them together, but the idea is that the input and output shafts are collinear, and they are directly beneath the jack shaft or this other shaft with the 2 gears on it. And we're getting a 2-to-1 ratio on both of these. So this is a 1.5 inch gear, 3 inch gear, same 1.5 inch gear, same 3 inch gear. All right, so that's what we're dealing with. Now let's go over here and try to sort out what is happening as far as the forces on these gears. These gears, by the way, have a 20-degree pressure angle. We'll do more about gears in the, I don't know, last third or so of the quarter, where we do a lot more of this, but there's a little bit we need to know right now just to get somewhere. So let's draw. Let's not use the very largest one. Let's use this one. All right, so this is going to be the 3 inch gear. And then directly below it is going to be, that one's more or less. Now I'm just drawing the pitch diameter here. I'm not drawing the teeth. That would be a bit extreme, so we're not going to do that. All right, here's our 3 inch gear and our 1.5 inch gear. Pitch diameter. If you actually took and measured the gear from outer tooth to outer tooth, you get larger than that. But this number is the pitch diameter where the contact occurs, and that's what we're interested in. So they both obviously have some kind of center point of rotation. I should have drawn that when I had the template on there, but I don't know, somewhere in there. And then this one's directly above it, somewhere right there. Now, the 20-degree pressure angle means that if we go back to this real quick, these teeth are not perfectly straight, right? In fact, this is a shape called an involute shape. We'll talk about that again when we get back to gears. But they don't, the way that they work, they don't apply force horizontally exclusively. Like the force isn't just horizontal here. Let's see if we can make these things on the screen more horizontal. And it's at a 20-degree angle. And there are 3 common 14.5, 20 degrees, and 25 degrees are the common pressure angles. It used to be, you know, back when people were hand making gears, that they were almost all custom made and there wasn't a standard. But now we have these 3 common pressure angles. So the 20 degrees would be, let's draw it in this color, something like this. So that's the 20 degrees. So this pressure angle means that if I take and find the components of this force, there is one component that is horizontal along this blue line. So I do have one component. I'm going to call that the tangential component. And then to create this angle, I would have a horizontal component, but I'd also have this, I'm going to call radial component. And this radial component is actually pushing on the gear, trying to move this gear away from this one. So too high of a pressure angle, and this force gets larger and larger, and that's generally not what you want. But it's going to push it away, and this one will have the opposite set of forces pushing it away. And so if you get them far enough away, they don't make contact anymore. In fact, on that same page, there's a list of maximum deflections for spur gears with different amount, and they also put a slope in here for uncrowned spur gear. So we'll talk about what that means later, but we do have uncrowned spur gears. Yeah, they're uncrowned. And so these deflections are really pretty small. Now these are in inches. I think I set everything in our simulation up in millimeters and stuff. Well, no, but I think it's going to give us, when we run the simulation, it's going to give us millimeters. So this is like 2/10 of a millimeter or 1/10 of a millimeter or something, not a lot. We're in this 11 to 19 pitch. We were at 16 teeth per inch, I think is what it said. And so we're right in that range, which is going to be not a lot of deflection, 0.1-ish millimeters. All right. So let's get back to this though. So I know, or I said, that we were trying to apply 10 foot-pounds of torque. So let's do this. That's going to be 10 foot-pounds, or 120 inch-pounds of torque. That torque gets transferred to this gear through this tangential force. So I can figure out this tangential force by knowing a couple of things. First of all, I know that this radius right here is half of the diameter, obviously. And that's this diameter was 1.5 inches, so this is 0.75 inch radius. So if I'm trying to generate 120 inch-pounds of torque, I've got a 1/2 inch radius, then I know a torque is a force, in this case the tangential force, times a distance, a perpendicular distance. So F times a 0.75 inch radius equals 120 inch-pounds. So I can back out what this tangential force is. So let's write those down. F tangential equals, F tangential times 0.75 inches equals 120 inch-pounds. Therefore, that tangential force, based on, I know I'm inputting 10 foot-pounds or 120 inch-pounds, 120 divided by 0.75, 160. So now that I know that this is 160 pounds, I can also figure out the radial force because I know the pressure angle. I know this resultant is at a 20-degree angle. I know that one component of it the horizontal component is 160 pounds, so I can calculate the radial component with tangent of 20 degrees equals this radial component over the tangential component. And I know that one is 160 pounds. So therefore, and I know 20 degrees, the radial component is equal to tangent 20 times 160, 58.2 pounds. Now, I'm going to, if I were to draw the free body diagram of just this part of it, which I didn't leave room to do, we'll just kind of put it over here smaller, I guess. It doesn't have to be the same size, just to have on the same sheet of paper though. I want to apply this tangential and radial force at the center of the shaft. So something, let's see where the center, somewhere in there. We're almost off the page. Let's scoot up a little. So this was 58.2 pounds. Put that over here. This was 160 pounds. And then since I moved, remember this 160 was down here creating rotation. So to have that same effect, I'm going to apply, or I'm going to, since I moved the 160 up to the center here, I'm going to put my torque on here. Now this one, that 160 right here, it has a radius or a moment arm, if you want to call it that, not of the 0.75 inches, and this is where we get our torque multiplication happening. Remember, this thing has a diameter of 3 inches, so this is a 1.5 inch radius. So this torque is that same 160 pounds that's acting between the two gears, but on this gear it's multiplied by 1.5 inches. So 160 times 1.5 is 240 inch-pounds. And you can also see, we kind of already said that. We said we had a 2-to-1 ratio between these gears. There's our 120 inch-pound input torque multiplied by 2, 240 inch-pounds on the other gear. All right, and we would need to do this same thing for the other set of gears, the same process. I've already done that, so I know the numbers. If I can find where I wrote them down, I think they're over here. Yeah, I think I see them. All right. So, but we need these forces so that we can, these forces are both trying to deflect the shaft. So let's go apply those to our model and see what's going to happen. Then we're about ready to simulate it. So we need to go back to SolidWorks. We're way zoomed in on our shaft. So we just did this set of gears. We would still need to do these. I've already done the numbers for them. The same exact process. Just the one thing that's different now. Let's go to this picture. So the one thing that's different now is that let's do blue for torque. Our torque, you know, it comes in, goes through this shaft. The torque is constant from this point, we're assuming, to this point. So that same, what was it, 240 inch-pounds of torque that we just calculated on this larger gear is the torque on this smaller gear now. And we go through basically treating it like the input to this. So there's our torque path right there, what it looks like. And we're assuming that there's no losses anywhere, which is an okay assumption. All right, so let's go back to our shaft deflection simulation, and hopefully it didn't erase everything. Oh, it looks like it did. All right, well, let's go to our new study, static. It's loading up. It should run a little faster when you're not trying to do a bunch of things at once. Let's hide that plane. That's that one that we created just for demo. So, all right, let's add our fixture. I should have saved it, I guess, but it's not that, doesn't take that long to add these, assuming it will let us. All right, there we go. On that surface, allow self-alignment, stabilize, check. Add one on the other end. On that surface, be sure you get the surface and not like the end or the ring or, you know, the edge, anything like that. It's the surface that the bearing would be riding on. Did it not do it? There it goes. All right. Now, our external loads. So this surface, these two, are the surfaces where the larger 3-inch gear is riding. And then these two, the gear and its hub. So I included that entire width. So we're going to do an external load. We're going to do a force. There is a bearing load, which might think that that's what you're supposed to do, but we're just going to do forces in X and Y. So I'm going to actually apply, the way I've split these, I'm going to do the top and bottom surface, although it's really only from the top, but we're going to do a selected direction. So in this pink box, I have to select some frame of reference. I'm going to go over here and pick my top plane, the one that's kind of horizontal through the shaft. I'm going to change the units to English since those are what I calculated these numbers in. These directions are in reference to the plane that I picked in this location. So I want this direct. Oh no, I don't want that direction. No. Let's see. I don't want that one. I want that one and that one, but I don't want them in those directions. So I want that. And those are actually pointing the right way. I don't really like that they're pointing on the bottom, but it's going to be the same. And then I don't want these units in here. So for the one that's going straight up, which is this one, that is the 58.2 pounds. This one is the 160 pounds. We don't apply the torque. We just apply the forces that are trying to deflect the thing. So those two, it looks kind of crazy with them pointing from both sides, but that's just the way it's set up. We could split this into more sections and just apply them on the side that we want to, but this will have the same effect. All right. And then we need to do the same thing over here. External loads, force. And I do want these split, though. This split line is important. You'll see it later on. English, selected direction. We don't want it normal. We don't want it pushing on that surface. We want it in certain directions. We'll use that top plane again as our reference. We want these two. All right, this one, the number for this one, and this is the actual correct direction. So when you work out the free body diagrams of everything, you'll see that this gear, the way that you have to think about, all right, what is the force on the gear, not the force that the gear is applying to the other one it's attached to. So the force on this gear would act in this direction, and it was 116.47 pounds when we calculated that. And that's the correct direction. This one is also pushing up, though, and it was, oh, wait, that's the 116. This force, the horizontal one, is 320. Okay. And then we'll check that. So there's our setup. with all of the forces and everything. And now I'm going to hide all of these. So view, hide all types, just so we don't have to get them in the way. Right click on mesh, and then you can go in and set up the mesh exactly how you want it. I'm just going to do mesh and run and let it do the default settings. All right, and there's our crazily deformed. Now you have to pay attention to our scale. This is, well, it's covered up. This is deformed at a 100:1 scale. So if we want to see what it actually deforms like, go to Displacement, Edit, Definition, and we can do a true scale. So true scale. Also, while we're here, make sure that our display is on this resultant displacement, not just, you can do just X, just Y, just Z, and forces and things like that. We want the resultant. We didn't, oh, because it didn't, there we go. So you can detect that it's, let's see if we look at it head on, if we see anything very tiny, but you can see these are not concentric. So you can see some amount of deflection at true scale, but there can't be a lot of amount of deflection anyway. All right, let's go back to our, whoops, that view. All right. Now, to figure out how much deflection we actually have, maybe you want to view the mesh. You can actually view the mesh over here, show mesh. There's the mesh on it. Let's show this. If you wanted to see if it looked like a bad mesh. Normally, when you're doing a finite element analysis, there's a whole process of mesh refinement, or at least testing for convergence. You run it at a low resolution and then a little bit higher resolution, meaning smaller elements. These little triangles are elements. I guess they're actually tetrahedron. But and get them gradually smaller and smaller, and then test what it is you're interested in, deflection or stress, von Mises, whatever it is, and plot that to see if it's converging to a solution or if it's just giving you kind of random numbers or they're oscillating or something like that. You don't necessarily get better results or even accurate results just by making the smallest element possible and running it. You could still have errors in the mesh the way it's calculated from the very beginning or the way you set it up. Your fixtures could be set up wrong or something like that. So normally we would do all of that process if we were trying to validate that this was a good simulation versus just taking the results that we get. We're just going to take the results we get right now, though, since we're not actually teaching a finite element class. All right. So let's right click on displacement, and there's this probe. I'm going to probe, and then I'm going to do on selected entities, and this is where I'm going to select those parting lines or split lines. I didn't put them on the bearings. If you put them on the bearings, you can't select that entire surface, and it kind of acts weird. So I won't have the slope of the piece inside the bearing, but I'll have right beside it, so that'll be good enough. I can update that. That'll generate a bunch of data over here. It's currently sorted by node number, which is, you didn't have any control over the node number. It just put the nodes out there, whatever order it thought was best. But you can also sort it by X. So that's what I want. The X direction for me, you can kind of see down here, is in the longitudinal direction of the shaft. So I want to sort by X. Well, let me show you what it looks like if you don't sort by X. So this little button lets you plot. And this is plotting the static displacement, and it's plotting the resultant displacement, but it looks crazy, right? So that doesn't look at all what you would expect. So let's sort by X. So just click on the X up here. Now I think I've inverted it, so I don't know if it matters which way we sort. And plot. And this is what you get. Let's make it bigger. You get this. You can also export these as a CSV file and do this in Excel, which you could certainly get the same information that you wanted from Excel. Now you do get a little bit of weirdness like right here and right here where those shoulders were, but that's okay. We get the general idea. So it looks like our maximum deflection is right here. Let's see, it's off your screen. Let me make this a little smaller. All right, down at the bottom, it shows the coordinates of wherever my crosshair is. So there it looks like the maximum, and we're at 0.38 millimeters, which is bad for us. Now at the gears would be, we'd have to have a marker where the gears were, but they're right in here. So at one gear, I am at 0.36 millimeters of deflection, and looking at my chart, whoops, dropped something over here. A little chart. Spur gears with teeth, a pitch of 16 can only have 0.05 inches of deflection, or else they've pulled the teeth too far apart. So 0.05, gotta find my calculator. Is that what fell? I don't think so. No. Where'd it go? Here it is. All right. 0.05 inches times 25.4 millimeters per inch. That's, I can only have 0.127 millimeters of deflection before this gear is going to be too far away from the mating gear. And so, and this is only one gear moving. The other gear is moving also, right, on its shaft. So I've got, 0.3 millimeters. So that would tell me right away that this shaft in this configuration won't work because the deflection is going to be too great and the gears are going to separate and they're going to skip or break the top off of a tooth or whatever. The other gear is somewhere over here, and it's 0.2 millimeters of deflection, so that's also too much. We can check the slopes. This looks like the worst slope. So if we're just doing it from here, then just do rise over run. So find you a point somewhere. This looks more or less linear up to there. So let's get a point here and write down those coordinates. So that's oh, be careful, it doesn't snap to the trace, so you can get coordinate points anywhere. Like these are giving me different numbers, so you actually want to make sure you're more or less on the trace. So this point is a y of 0.18. I'm not going to be too accurate there. X of 130, and then down here somewhere, let's get on the graph, y of 0.06, these are millimeters, and x of 141, let's do 142. All right, so our rise is 0.18 minus 0.06, and our run is 12, 142 minus 130. That gives us a rise over run of 0.01. So that would be, if we did the tangent of that, that would give us 0.01 also. If we were in radians, I guess. Yeah, so it gives us 0.01, a bunch of zeros, and a 1. And our maximum, let's see, slope, let's get that in there. It's this one, spherical ball. We're actually okay there. It said we can be at oh, these are radians. 0.02 radians, and we're at, we were at 0.01, or is that degrees? Oh, that was degrees though. So we might be out of range on that too. No, we're okay there, I think. Although I don't, let me see. If we did, I need to do inverse tangent of that. That's the problem. Oh yeah, we're at 0.57 degrees. I did tangent, not inverse tangent. to get the angle. So we're at 0.57 degrees, which is more than 0.026 radians. I'm pretty sure. Let's see. That would be if we 0.57 degrees convert to radians. So times pi divided by 180. No, we're okay. We're okay on that. All right. And this other end looks like an even smaller slope, so we would be even better over there. And again, you would probably rather export all of this into Excel, which you could do right here. Just save that data as a CSV. Yeah, your only option is CSV or text file. And then you can do whatever you want with it. You can calculate the entire slope everywhere, plot that. You can plot the shape of the beam or the shaft and everything, but our deflection was too great. So if your deflection turns out too great, your book does have a relatively simple solution for that. So on page, in the 10th edition, on page 373 down here, equation 717 and 718. Let's see if we can make those a little bigger. These are two different equations you can use depending on if you want to redesign, well, not redesign, reshape, resize the shaft based on deflection or based on slope. And so you have the old deflection or old slope right there, dy dx. You have the allowable, what you're going to allow for the slope or deflection. You have a design factor, so a factor of safety. And this 1 to the 4th has to do with, remember last time we said that deflection was not material dependent, at least in general, because most all the materials that we're going to use are steel, which have more or less or the same modulus of elasticity. So if you have a different material, obviously you could change this by changing materials. But most shafts are going to be just a steel, which has pretty constant modulus of elasticity. So we have to change the size of it. So it's giving you a new diameter at this location. And once you have that diameter, based on the step sizes you need for the shoulders and things like that, you can redesign the whole shaft based on this ratio. So this 1/4 power is from the moment of inertia of that diameter shaft. Again, this only is for solid round shafts. If you have a different shape or a hollow shaft, then this won't quite be the same. But that's an easy way. Let's see, there's one other equation. What was it? Oh, the other part of this, the last part of this chapter over here talks about really short shafts. So it could be with a really short shaft, and we do have in our model here, oh, I should have saved that, I suppose. Or maybe I need to, there we go, check out of it. So this potentially could be a short, and maybe this could be a short shaft. They give, I think it's 10 to 1 diameter to length. Well, 1 to 10 that way. If your diameter is less than 1/10 of the length of the shaft, then you might have a short shaft. I think I said that correctly. So the thing that can happen with a short shaft, one that is defined to be short, is that maybe it doesn't deflect, but it just shears, like it just breaks off. Because normally you ignore that transverse shear component because there's way more things happening stress and deflection wise. But on a really short shaft, maybe the stress and deflection aren't that big a deal because it's short. And what starts to dominate is the direct shear of that shaft, and you just have to check that also. So that's the very last mention in the chapter 7.5 is being sure to check for direct shear of the shaft. It just breaks through shear. So that would be kind of like if it broke on, let's see, where am I at? Oh, I'm in an assembly right now. Well, so if it broke right here, you know, kind of right there, or right back there somewhere, it just sheared. So that is a possibility with a shorter shaft. And that's the last part of that book, or last part of that chapter. Other things to consider are, actually, I think we've talked about all the things to consider. I think that's more or less the procedure for doing this. I don't think there's any other bits to it. Well, other than the fact that this is all just for deflection, you still have the stress analysis. So you could be completely fine on deflection and fail in stress, fatigue failure. Or vice versa. You could be completely fine on fatigue stresses and fail in deflection. So you do have to think of both of these at the same time. And like I said, a lot of times the deflection is going to be difficult to do by hand. You can get a rough estimate by taking the thinner diameter as the whole size of the shaft. And if it passes that way, then making it bigger for the steps and the shoulders and all that is not going to make it fail. It's going to make it fine. So you could do a really quick, if you had to do it by hand, you could do a thinner diameter shaft that's just that constant diameter of the thin part of your shaft. See if that passes the deflection. And in that case, you just do shear and bending diagrams and find out. Or, well, you could, no, not that. You would do the shear and bending diagrams to calculate the bending moment at the point to calculate the stress. But you would do just a superimposed 2-point loads, in this case, on a beam to figure out the deflection. And if it was okay with being just the thin part, then it's certainly okay if it's thicker somewhere. So you could do it that way by hand. But the SolidWorks simulation is not difficult. I haven't done this in Fusion 360, but I assume it is similar process. Maybe I'll try to fire that up sometime and see if it's more or less the same. It is going to be similar at least. But what you're trying to get, the couple of things to remember are you want to design your shaft in a way that you're going to be able to apply the right fixtures and loads where you want them. And so in this case, it means putting in those split lines so that I can select certain faces for a fixture or for a load. If I don't have this face defined, when I go to put a load here, it's going to put it on the entire face, and so then I have to. That's not going to work. I want it in just certain locations, and so I do that with using split lines. There might be another way that you have that's simpler. Most of the time, you don't have to simulate the assembly, like with the gears and the bearings and everything on there. You just take the shaft and put the forces on it. You don't have to model in the fillets. In fact, if you do model in the fillets, then you have to be careful with your mesh. In fact, let's well, it'll take too long. We don't have enough time left to do it. But what can happen is if I put a fillet in here, let's put one. So if I put, that's way too much fillet, but if I put a fillet on there, now this curved surface, when I go to put those triangular tetrahedron elements to mesh it, they need to be smaller in here to account for this curve. And so now either I have to have smaller elements everywhere, which may or may not be a good thing, or I have to have an adaptive mesh where it's smaller here and gets larger over here. So it actually creates a little bit extra complications when you create the fillets and the ring grooves and the keyways and all that kind of stuff. I'm going to delete that. All right, I'm going to try to post a link to where you can download this. I'll put it in the video description, and I'll put it on Moodle too. I know I can put it there. I probably shouldn't post the SolidWorks files of the bearings and gears, but I'll link to where you can get them because they're just off of McMaster. You can just download those, and then that way you can assemble this thing. The other shafts here are the shorter shafts. They're nothing special at all. I think I just made them up. All of this is made up, I guess, but that way you can play around with this and try to get your simulation running. You do have a homework assignment to create a SolidWorks simulation like this. All right, we actually have some time left. I don't see any questions. I think I'm on the live. Yeah, I'm on the live chat here. So if you have any questions, let me know. But I don't think we have enough time to do a whole new thing, and I don't think we have any little short pieces left unless there's a question to answer about any of this. But I guess I should open Discord, see if anybody posted a question over there. I didn't see any. No, I don't see any over there. All right. I think we're good. I will close out this stream, and I'll post these, or a link to this model at least, and I'll post the shorter shafts also there. They're actually, the two are the same thing, so you just use it twice. And then I'll link to the McMaster pieces that you can add to this, or you can create your own. And that way you'll have to assemble it together. Maybe I could, I don't know if I would be able to get the assembly to load up without also packaging in the McMaster parts, which I don't want to do. All right, I will see you guys on Monday. We'll do one more thing about shafts. Basically, we'll talk about all these other pieces like keyways, ring grooves, set screws, the keys themselves, all that kind of stuff. Oh, there's a question about the SolidWorks homework, how detailed I want the assembly. I don't want it detailed. Like, you don't have to draw, some of them have ball bearings in there, right? So I don't think you have to draw individual ball bearings. You could do like I did and just go grab a ball bearing from McMaster and build around that. I mainly want to see, the book has lots of cutaways and quarter drawings and things like that. So I mainly want to see that you're able to interpret what they really look like is the main point. Because it uses that a lot throughout the whole book, that style where there's a cutaway that's not showing the whole geometry or whatever. So I don't want a lot of detail, just that you can show me that you understand what these things look like in real life, more or less, without all the little details. Just the gross, kind of like what I did here. You don't have to do fillets, just some steps. I think these are all shafts of some sort. So the shaft, maybe a step. If you want to put a McMaster bearing in there, that's fine. If you want to create your own bearing, then just make a cylinder for the bearing. It'll be fine. So it'll be good. All right. If you have other questions, let me know. Send an email. Put it in Discord. Whatever you want. I'll see y'all Monday.